So, welcome back. Today's lecture actually I have decided to uh, talk about the computer arithmetic, the floating point numbers, the way we do computing in a computer. I think this topic I have been feeling uncomfortable when I have taught you gram-skimmed gram-skimmed orthogonalization, the modified gram-skimmed orthogonalization. We discussed a bit about the overflow problems, I think, in householders, and in the givens rotation again, I am going to discuss about it. We talked about cancellation errors, in modified gram-skimmed and gram-skimmed methods. So we have not been able to dive deep into understanding the problems here because we have really not tried to touch upon, not tried to dive deep into the floating point number system that the computers use. And initially, I was not like so keen to start with it with this topic because then it looks a bit dry, though this is the right way. Usually books start from this point, first and then go deeper into algorithms. But in my opinion, to make it more interesting and lively, for a long time I said, okay, let's not worry too much about, um, the nitty-gritties of computer arithmetic, and as if we are doing with infinite precision, let's first develop some basic beautiful decompositions like QR and SVD that we have already covered. But as we have been doing algorithms, we are automatically touching upon one way or other, discussing and touching upon this aspect of floating point number systems and their problems. So I think post midsem, this is the right time now to go a bit deeper into it and then again come back to algorithms so that in this in the next half of this uh, lectures, post midsem lectures, you would appreciate this aspect and the way we take care of it in the algorithms. So to start with, basically floating point numbers, what are they trying to do? So today I want to actually like look into floating point numbers. What is the IEEE standard way of representing it? Why do we do normalization? Properties of floating point system and time permitting rounding. Otherwise, rounding, we will start from rounding onwards in our next lecture. So, uh, our idea is that we want to, when we talk of floating point numbers, basically we want to represent real numbers are in a machine or computer. And a machine or a computer, because it is it is a digital device and has finite precision, it can only represent a what I would say approximation or a discrete version of R, and that too within some limits, the lower limits and upper limits. So you basically have, let's say you have a p digit. P is the level of the precision. So I have a p digits number. So the first one is D0, second digit is D1, third is D2, and the last one is DP minus 1. So let's say this is a number, and in the number system the base is beta. It's also called radix, and of course I did say that P is precision. So 8-bit, 16-bit word, 32-bit, single precision, double precision, like that. And the exponents have a range L to U. So L is the lower limit and upper limit. This is for the exponent. So what I mean to say is this number x is represented as, it could be plus or positive or negative. We will have a, usually in a computer we will have a sign bit for this. D0 plus D1 by beta plus D2 by beta square, so on up to dp minus 1 by beta p to the power minus 1 into p to the power e. So this is what usually this number signifies. So I think you should read this number as, you must be thinking why what is this funny thing going on. You should read this number as d0 dot d1 d2 d3 to dp minus 1 into beta to the power e. This is what this x is representing. So this comes after the decimal, so therefore it comes with a weight 1 by beta. This is the second one after the decimal, so it comes with a weight 1 by beta square. This is the last one after the decimal, so this comes with a weight of 1 by beta p to the power minus 1. And d0, d1 to d3 are digits. So for example, if you are, like for example, you are in a calculator, beta would be like a HP calculator. It uses 10 digit system, so beta would be like 10, and so the DIs here are going to be 0, 1, 2 to anything from 0, 1, 2 to 9. In a traditionally computers, especially those who have properly implemented the IEEE standards, the DI would be base would be 2, and so the choices of the digits are going to be only 0 or 1. Now a thought must have come to your mind, that why did I choose this specific way of representing a number. Why did I go for this specific way of representing a number? So the idea is that this floating point number system basically resembles what we have in the scientific notation. You must have studied in your, probably, I don't know, school level or somewhere else in the science classes or experiments where we discuss the scientific notation. So it's very much motivated from there. And here the idea is that whether the number is, even if a number is very large or very small, doesn't matter, it can be represented as a number of moderate size times appropriate power of 10. For example, suppose you had 98751, let's say. So you could represent this as 9.8751 into 10 to the power 4. So this is a number of moderate size and times appropriate power of 10 to the power 4. Or suppose you have a number 1, 2, 3, 4 5 1. Let's say this is your number. So this you could represent it as 5.1 into 10 to the power 1, 2, 3, 4, 5. So 10 to the power minus of 5. Now these are numbers of moderate size. These are numbers of moderate size, and you can add up. If you want to maintain 1, 2, 3, 4 digits, then 3 and 4. These are numbers of moderate size, and uh, they are to be scaled by appropriate power of 10. Now, because this point is floating, you could have 51 into this 10 to the power minus 4 or 98 into 10 to the power 3 or whatever. So because this is floating in this particular way, or you could have it 0.9 into 10 to the power 5 or 0.5 shift it here and 10 to the power 6. So because of this, such numbers are called as decimal point is floating. So it is called as floating point number system. Now for the purpose of efficiency, and standardization, usually what we will try to do is fix this location of the decimal digit. We will fix this location of the decimal digit. So the most common thing to do is, as I showed it to you here, the leading digit should be greater than 0. So that's why my number is D0 dot D1, D2, D3 and so on, and this D0 should be not 0. D0 should be, unless the number is 0, the D0 should not be equal to 0. So if you do that, then what happens is you normalize, and this improves the efficiency of the representation system, and this is the most common thing that is usually done. I mean, this is normalization, and I would almost say that it is so to say mandatory for us. Otherwise, suppose like, to give you an example, suppose I decided to bring this decimal point somewhere here, then the same number, I mean, I could have written like this: 1, 2, 3, 4, 9 into 10 to the power maybe 8. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I've taken too many digits here. 1 minute. Okay, so 1, 2, 3, 1. Let me give me one digit. 9. So 1, 2, 3, 4. So this will become probably 10 to the power 7 would suffice. This would give you another representation, approximate representation of this number, but you can easily see that you are losing a lot of accuracy here, because you have allowed too many of these zeros. So by forcing this leading digit to be non-zero, we make best use of all the remaining digits in our representation. So that is why we have fixed in our the format as D0 dot D1, D2, D3 into beta to the power E, where D0 is not equal to 0. If it is a binary number system, then obviously what does that mean? There are only two choices, 0 and 1. So the D0 will become equal to 1 only unless the number is 0. And this, if you remember this implement, if you know that, then you don't really need to keep one bit separately and always keep a 1 there unless the number is 0. So 0 number has anyway a special representation where everything is set to 0, including whatever is kept for these exponent bits, so those are also set to 0. So 0 has a special representation, and for all non-zero numbers, this is the representation. So now you can actually need not keep this bit actually 1 and then set everything else. You can implicitly remember it in your algorithms and use this bit to increase the accuracy of your number system. So such kind of tweaks also you can do. So this thing D0, this number which I have written here, this is actually called the mantissa. This is actually called the mantissa. And exponent, of course, we have already discussed the exponent. And if you come to the IEEE, for example, single precision system, beta will be 2, precision will be 24, so D0, D1 up to D23. Lower limit is set to minus 126 for the exponent, and upper limit is set to 127. So this comes from basically 2 to the power 5 is 32, 2 to the power 6 is 64, 2 to the power 7 is 2 to the power 5 is 32, 2 to the power 6 is 64, 2 to the power 7 is 128, and you add one sign bit. So basically a 8-bit which is a byte you are keeping here for representing the exponent. And I think in a 2 complement system, the numbers that would be represented will be, the range will be from minus 126 to 127. Now the same, this prior to IEEE standardizing it, computers were using different kinds of systems. So for example, Cray, HP calculator, as I said, uses 10, IBM mainframe was using 16, and Cray uses 2. Precision in an IBM mainframe was 6. Cray computer had 48, and so on. And so they are different ones. So this creates a problem, and the representation is different. So writing good generic scientific libraries, computation libraries becomes a problem. But if everybody does internally, now everyone does it also internally, the computation using IEEE single precision or double precision, then the standard libraries work across the different formats. So in the double precision, it is 53 bits are available. P is not 24, so it's D0. It's not D0 to, here it is D0 to D23. Here it is D0 to D52. And the lower limit here is minus 1022, and the upper limit is 1023. So this is the IEEE double digit. I'm sorry, the double precision system. Now let us come to the topic of normalization. I already started discussing with you, but to sort of add properly to it, in the normalization, the leading digit D0 is always non-zero. So if beta is 2, then it means D0 has to be always 1. That's the most common thing. And therefore, in a normalized floating point system, such a normalized floating point system, the mantissa M, what is the mantissa? Remember, this here is your mantissa. The mantissa M will have a value between 1 included, and strictly less than beta. Let's check this up. So you remember, this is how it is d1 d0 to dp minus 1. So if this is always 1, if I set all this to 0, then the number will become basically 1, which is the lower limit above. And if you look at the largest one possible number there for the mantissa, then you should set all of this to 1, which basically means that your number is going to be, what is it going to be? Largest number. So D0 can take a value from 0 to 1 to beta minus 1, right? So for example, if beta is 10, then the D0 can, or any of those bits can, I'm sorry, so in fact, this one is specifically for binary. If you had, say, beta equal to 10, then you could, lowest is correct, but the beta is 10, for example, then you could set all of them to 9999. If beta is 2, then you can set it to all to 1111. So therefore, the beta range is basically the digits range from 0 to di's range from 0 to beta I minus 1. Range from beta I minus 1. So if you actually sum all this number together, what is it that you are going to get? Beta minus 1 into 1.11111, taking that largest number, and on the scale of, on the base of beta. So this is beta minus 1 into 1 plus 1 by beta plus 1 by beta square up to 1 by beta p minus 1. So you can see that it's a geometric series. So therefore 1 in a into 1 minus r to the power n, r is beta to the power minus 1, n is p precision, so 1 minus beta to the power minus 1 to the power p, that is 1 minus beta to the power p, divided by 1 minus r. The geometric series, our ratio r is this, number of terms are p, and so this largest possible number will come out to be this, which if you simplify this, I'm sorry, if you simplify this is beta minus 1 by beta. So beta minus 1 will cancel, beta will go upstairs. So therefore max is going to be 1 minus largest positive number. This is going to be 1 beta into 1 minus, which is strictly, so this is strictly less than 1. So therefore this whole thing is strictly less than beta. So this is strictly less than beta. Hence I said that the mantissa satisfies the property of this, where the this is the this is the range for your, this fixes your range for the mantissa. It is minimum value is 1 and the maximum value is always below beta. It's actually this, strictly less than beta. So, so if you have like beta is 10, base is 10, then mantissa in our representation will always be between 1 to 10. If the if uh, it is 2, beta is 2, then it is between 1 and strictly less than 2. How much less than 2 is coming out from this term? This is beta minus beta to the power minus of p minus 1. So this term tells you how much lesser than beta it is going to be. Higher the precision, more closer it comes to beta. Now, what are the advantages of normalization? So advantages of normalization is number one, and very important, the representation of each number is unique. Is it not? Representation of each number is unique. Two, no digits are wasted. This I have illustrated to you earlier. Wasted on leading zeros. Unnecessary. I showed you earlier. The zeros, thereby maximizing precision. Third, in a binary system where beta is equal, if beta is equal to 2, then the leading bit is always 1. This also I have said. D0 is always 1, so it need not be stored, thereby obtaining, gaining one extra bit of precision for a given field width. This discussion is, of course, from the book that I like a lot, Scientific Computation Introductory Survey, Michael Heath. Now, these are, so normalization, leading bit should always be set to 1 if it is a binary representation, non-zero in general, and now we have seen what's the range of the number. Now let's come to some more properties of the floating point system. So let's explore additional properties of floating point system. First thing is the number of normalized floating point numbers. So how many are the number of normalized floating point numbers in a given floating point number system? So this number is 2. So remember, this is d0, d1, d2 to dp minus 1 into beta to the power exponent, where e comes from L and U, and this number could be plus and minus. So for this thing, that for as many plus, so many minus, so therefore 2 times is taken for this particular thing, 2, and then the choices on D0 are, because see the D0, strictly speaking, you can have it from 1 to up to beta minus 1, but 0 is not possible in the normalized system. This choice is out. In the normalized system, 0 is not possible because the leading digit has to be 1. So therefore, how many choices are available here? Beta minus 1. So therefore, beta minus 1. Now each of these ones can be 0, 1 and 2 up to beta minus 1. So beta choices are available. Again beta choices, again beta choices. So therefore, the possible combinations are beta into beta into beta and so on up to beta p minus 1 times. So therefore, you will get the next term here as beta to the power p minus 1. And this is for every specific choice of, all this can be done for every specific choice of E. And how much is the choice of E available? U minus L plus 1. This is the choice which is available to you. So therefore, these non-zero numbers are so many in place because the leading digit is 1. All of these are non-zero numbers plus a number 0 which has a unique representation. So therefore plus 1. So this means that the number of normalized floating point numbers given a base, upper limits and lower limits on the exponent is this. These are the anything lower than this and anything bigger than this cannot be represented in our system. So therefore the next question is, if the number is non-zero, what is the smallest positive normalized floating point number that can be represented? And similarly, what is the largest positive normalized floating point number that can be represented? The smallest number, it is actually called as underflow level. It will correspond to 1. This has to be compulsorily 1 and everything else should be 0. So therefore, and if you want to go to the smallest one, then the exponent should be set to the lowest value. So therefore, the underflow level is going to be simply D0 comes with what weightage? With unit weight. Remember, D0 comes with unit weight. So therefore, the underflow level is just going to be, looking at this, the number underflow level is simply beta to the power L. This is what is the underflow level. Now, what is the overflow level? Now, what is the overflow level or OFL? So, here it's clear that you want to set the largest possible number, so everything should be 1 and E should be set to L. So therefore you would write this number as 1.11111 to the beta into beta to the power U. So this is going to be 1 plus 1 by beta and so on up to 1 by beta p to the power minus 1, I'm sorry, not 1, into beta minus 1, because I'm sorry, this I somehow always think in terms of binary numbers, the first thing, but I'm keeping the discussion generic. So therefore di's have a range from 0, 0, 1, 2 and so on up to beta minus 1. So therefore the numbers are beta minus 1 dot, again beta minus 1, beta comma beta minus 1 and so on and so forth. So I take beta minus 1 common. Like for example, in a decimal thing it is 9.9999, and suppose 10 is the base and highest level is suppose 1023, let just for the sake of discussion, then this is the largest possible number that we are going to have, and 9 is nothing but 10 minus 1, which is beta. So I take that as common, then it becomes 1.1111 1.1111 into beta to the power u, which is expanded as follows into beta to the power u, and now you write the geometric progression for it. So 1 r is beta to the power minus 1, so r to the power n is beta to the power minus p, because n is equal to p. So beta to the power minus b divided by 1 minus beta into beta to the power u. So beta minus 1 will cancel out, and therefore you will get this as beta into 1 minus beta to the power minus p into beta to the power u, which is beta to the power u plus 1 into 1 minus beta to the power minus p. This sets your overflow level. So to say again, putting it, underflow level is beta to the power L, like L could be minus 1023 for example, and beta could be 2. In a if you go for IEEE single precision, then L is minus 126. So beta into beta will be 2 to the power minus 120 in IEEE single precision. This underflow limit is going to be equal to 2 into 10 to the power minus 126. So no number smaller than this can be stored here, and OFL is 2, upper limit is 127 plus 1, so 128 into 1 minus 2 to the power minus p is 2 to the power p is 24, so 1 minus 1 to the power minus 24. So anything which is between this and can be represented, can be approximated, and we will look into rounding rules, chopping to the nearest. We'll look at those things later on, but this is the range of non-zero numbers which can be represented. Anything beyond this cannot be represented, so you have crossed the overflow limit as it is crossed. So we say that now there is a overflow, and if the number is between 0 and 0 to the power minus 120, 2 to the power minus 126 and 0, then in this range nothing can be pictured. So after this it will either go to 0, or it will be set to this value, so it will go to 0, which means you are not able to pick it up, which is therefore called as the underflow level. So bigger this single precision, double precision, more in general, I would always say that if you can do your computation in double precision, do it. Means, of course, if you are writing a very generic library, critical mission and all that, you should do it in double precision and keep yourself as safe as possible. Now that you have known this underflow and level and overflow level, you will be more easy to discuss some of these issues, including cancellation, which I will take up in the next lecture. Now I want to close this talk, today's lecture, with a discussion on with an example which brings out a very interesting property of I'm taking a toy. I'm sorry. I'm taking a toy representation example of a floating point system. So with beta equal to 2, precision equal to 3, and L equal to -1 and U equal to 1. So therefore, if you look at its OFL, the largest possible number is with a 3-bit precision D0, D1, D2, so 1.11 base 2, and the upper limit U is 1, so into 2 to the power 1. So this is nothing but 3.5 on the scale of 10. And if you look at the upper flow limit here, the underflow limit, not the overflow, the underflow, and both these bits you will set to 0. The D0 bit anyway has to be set to 1, and the exponent should be set to the lowest value. So therefore 2 to the power -1, which is 0.5 into to the power 10. And if you look at the possible total numbers, which are number of normalized floating point numbers, then it is going to be 2 into beta -1, which is 2 minus 1, into 2 beta 2 to the power p minus 1. So 3 minus 1 is going to be 2 into u minus L plus 1. So therefore 1 minus of 1 plus 1 plus 1. So this is how much? This is 8 into 3, 24 plus 1. That means in this toy system, there are 25 discrete numbers which are possible to be represented, and they cover a range of 0.5 to 3.5. This is the range that it covers. Similarly, it will cover minus of 0.5 to minus of 3.5 and 0. So 12 numbers here, 1 0 number sitting in the center. So this is what I have shown here in this 0, 3.5, 3.5, and you can see symmetric. You can see that it is symmetric on this side and this side, and you can count now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So exactly all the 25 numbers are shown here, and this is the only small range of real line that can be covered in it. Now, one thing which you would notice, I'm sure you would have noticed it, all of you are damn smart, I know that these numbers are not uniformly spaced, is it not? So the first UFL is what? 0.5. So between 0 to 0.5, there is nothing possible. So between 0 to 0.5, there is nothing possible. Similarly, this is minus 0.5. So there is a big gap here. But then you can see that there are a cluster of these numbers which are coming here, and then they look a bit more spaced out, but the pattern is similar, but they look more spaced out. and then you come here. Between 3 and 3.5 there is a big gap sitting here, but here they are somewhat closer, and so it's a non-uniform thing. This is expected, right? Because you are not having a arithmetic, your number system is not like this. If you had a number system which looked like a arithmetic progression, then they would come beautifully spaced, evenly spaced out on this line. But our number system is like d0 plus d1 by beta plus d2 by beta square into, so we have in fact precision is 3 and beta is 2, so therefore I would write like this: beta to the power e, and this e can be 3 choices minus 1, 1, 0. So whatever we study in this representation, the spacing, whatever the spacing we study here, that same spacing, but with a multiplication factor of this, will change for when I start from, say I start from beta equal to 0. So then I'll get this picture. Then when I make beta equal to 1, again this, but amplified by a factor of beta, you will again see the similar picture which is coming. So therefore, very, very important to note that the numbers are discrete, but those 25 numbers are not uniformly spaced, they are unevenly spaced. Now we have understood that the first number, we have understood why it is this big gap is lying here, because this is the underflow limit. Now let's try to understand the next number after this. So in my system, 1.00, after this the next number is going to be 1.01, then the next number is going to be 1.10, and then the fourth number is going to be 1.11. So I'll get 4 choices with the 2 digits that I have got to play: 0.5, which is this choice, 0.5, which is this choice, and then 3 more choices: 1, 2, 3. So these 4 choices are what I am going to get with with keeping this, keeping this exponent fixed. And where I have fixed the exponent right now? I have fixed the exponent to beta equal to e is equal to exponent I have fixed to 0. So the first number is obviously 0.5. The second number is going to be half plus this will get a weightage of 1/4, but this is, I have set 0 to it. So therefore plus the next one will be 1/8, which is 3/8. So this is which is 5/8. So this is 4/8. Then the next number becomes 5/8. Then 1/2 plus 1/4. So if you take 4, this is 6/8. And then now it's easy for you to guess what is this going to be. So 4 plus 2, 6 plus 1, 7/8. So 4, 5, 6, 7 uniformly distributed with a distance of 1/8. So half or 4/8, 5/8, 6/8, 7/8. You can see this uniform one, and then after that you set this bit to again 1.5 0.000, and now you take the multiplication factor of, I'm sorry, this I did with, I'm really sorry, this I did with e taken as minus 1. That is why d0 into half gave me 0.5. So e taken here was minus 1. Then you will see that after this, when you set e to 0, then you will get 1.000, I'm sorry, 1.00, the smallest number, into 2 to the power 0, which is 1, and then you get again the 4 choices. So 1, 2, 3, 4, so 8 numbers are there. Like that, 9, 10, 11, 12, like that you go. So the largest number is 3.5. If you calculate the previous number to it, and I leave it to you to check it out. If you calculate, now I have explained it to it quite well. If you calculate the previous number to it, it is going to come out to be 3. So you can see that here the spacing is small, here the spacing is large, here the spacing is large. So this is another very interesting part of the floating point system, that the numbers are not uniformly spaced. This you don't see when we write our algorithms, but you should make a very you should make a note of this. And this is a very tiny toy system, but it is in fact it shows the characteristic of a floating point system in general, which is that at a sufficiently high level of magnification, every normalized floating system looks essentially like this one, grainy and unequally spaced. So I'll have a small discussion on rounding, and uh, then uh, we will close our, or maybe I'll discuss, we'll start from rounding in the next class. So let's take a break here. Thank you.